The name is Nicolai Jensen. I'm a student at Aalborg University, Copenhagen with focus on Medialogy. The topic I'll address today is image processing and a few different filters that you can apply to an image or a video feed, as I have here. Firstly, a brief explanation on how images work. An image consists of a lot of pixels. In this case, in this video feed, we have assigned the width to be 320 and the height to be 240, which gives us a total amount of 76,800 pixels. You just multiply those two, and each pixel have three different color channels: red, green, and blue RGB, which combined gives us this image. Gives us the image that we see on a webcam feed, or an image in general. And as you may know, video is sort of like it is actually a lot of images played rapidly to create this moving image. Alright, moving on to the filter. This filter is called color channel segregation, which pretty much just prints out the red, or the green, or the blue channels. Yep. Alright, let's move on to the header file. Firstly, I will explain how I fetch the video. I use this off video grabber that I call video feed. You can call whatever you want. And I set the video feed's verbose to true and the init grabber to width and height. Then I update it, and then I draw it on 0, 0. This is pretty basic, but this gives us the non-altered image that you saw on the left. Alright, moving on to the altered ones. Here in the header file, you set an off texture for each and every one of the images that you have on display. Right here I have 3 images because I have a red, green, and blue channel. And make an output for all of them, unsigned char pointer output. Right here. Alright. In here I set the output to be a new unsigned char, which contains the values of the width, height, and the 3 different color channels. And I do this for each and every one of the outputs. Then I set the video texture to allocate with width, height, and the RGB scheme. And right here, I actually apply the alteration that you saw. I will get back to that in a moment. The important thing to know is that I changed the output right here for each frame of them, for each picture of them. Here I load the output, width and height and RGB scheme into the video texture, and right here I draw it. I draw it on width +5 because this is how big the image is, and this is where it's gonna draw it. Width because I already have one image on 0. That means I have to go right next to it with width, and +5 because I want to have it a little border, 5 pixel border. Yeah, you kind of get a picture. Alright, moving on to the alteration. Here I say if the video feed is a new frame, I have to do this right here. Then I make an unsigned char pointer that is pixels, which pretty much fetch the video feed's pixels. Then I make a double for loop right here. First for the y-axis, which goes from 0 to the height and adds 1 to the y-axis for each time. For each time it goes, yeah. You kind of get the picture. And the same for the x-axis. You can pretty much say that for each time it runs down the y-axis, it has to go from the beginning to the end of the x-axis, which is pretty much like how you read a book. When this is done, it goes from pixel to pixel to pixel to pixel to pixel, and so on. For each time I encounter a pixel, I have to apply this. This is a normal formula for the red channel, and this is for the green channel, and this is for the blue channel, which pretty much gives us the value for the output, and it sets it to be equal to this, which is the red channel again, and 0. The values for the pixels is between 0 and 255, whereas 0 is black and 255 is white. So we set the green and blue channel to be equal to black, which pretty much removes it, and we only print out the red channel. Alright, and for each picture we do the same, but only with for instance in here we only print out the green channel. So here we have an inverted picture of me. As you can see, all the dark colors are getting lighter and all the light colors are getting darker. Alright, so how did I do that? It's actually pretty simple. Instead of using 2 for loops, a double for loop, we only use 1 for loop. We make a new integer that we call total pixels and set it to be equal to width, height, and the 3 different color channels multiplied with each other. Alright, then we say for I equals 0 to total pixels, we add 1 to I. And right here, as I stated before, the highest value is 255, which is light. And if we subtract the current pixel from that number, we get the inverted picture. Because if we have a black pixel here, for instance, that we have 0, that's 255 minus 0, which gives 255, which gives a white pixel. This is the mirror filter. As you can see, I'm clearly being mirrored to the other side. Alright, let's take a look at the code. Here we have a triple for loop. One for the y-axis, one for the x-axis, and one for the color channels. Alright, as you can see, this code, it is y times width plus x. Instead of writing that over here, we have y times v plus, and then we have the width minus x, which gives us the mirrored effect. This is the simple brightness filter. And as you can see, there is nothing changed right now because we start at 0. You have to use the arrow keys to actually move the brightness up or move it down. Simply by up and down. So let's take a look at the code. We have new things in the header file. We have the function called keyPressed, and we have a new float called brightness. We set brightness in the beginning to be equal to 0 because we want nothing altered from the beginning, but we want to be able to alter it through the keys. So we make a switch case within keyPressed, which says that if you push up, you add 1 to brightness, and it cannot go higher than 100. If you push down, you subtract 1 from brightness, and it cannot go lower than minus 100. Alright, so how did I do that? Just like with invert, we have a new int called total pixels, and we use a single for loop. Right here, instead of minus 255 with the pixels, we just take the pixels and add the brightness. And this is only a couple of if statements stating that if the value is higher than 255, because it cannot get higher than that, then the value has to be 255. And if it's lower than 0, it has to be 0. And then we set the output to the new pixels that we created up. This is a simple contrast filter. Like the simple brightness filter, this also can be changed. The value of the contrast can be changed by the arrow keys. So if you push the arrow key up, the contrast will go up. If you push it down, the contrast will go down, which looks kind of weird, but that's how it's supposed to work. Let's have a look at the code. First of all, in the header file, we have some variables a float called contrast and new contrast, unsigned jar called RG and B, and a double called pixel R, pixel G, and pixel B. Alright. First of all, the new contrast is the one that we are gonna manipulate with the key pressed switch case. I will not go through that again because I already did it in brightness. We set all the variables to be equal to 0. And then right here we have a double for loop for the x and y axis. And then we set the RG and B to be equal to the red channel, green channel, and blue channel respectively. Then we have a formula for the contrast, which includes the new contrast, which is the manipulated one. And then we have a formula for the red channel that we're gonna print out. Then we have a precaution here that states that the value cannot go below 0, or otherwise it's equal to 0, and it cannot go above 255. And then we print out the red channel, and we do that for the green channel and blue channel as well. Alright, here we have the order contrast, and I will show you. You can see the contrast has been drastically increased, and I will show how I did that. First of all, we have the float RGB right here, and then we have two for loops for the y-axis and x-axis, and we have set the RGB to be equal to the red channel, green channel, and blue channel respectively. Then we have this one which says that if the red channel is higher than or equal to 100, and red channel is lower than 250 or equal to 255 minus 20. The reason we say minus 20 is because of the next step. Is we add 20 to the red channel, which makes if we have 255, it will be 275, and that can simply not compute. Then we have an else if statement to correct the pixels above with the value above 235, which this gives to be equal to 255, as 235 actually is 255 in this case. So instead of if we for example have 236, we add only 90 to it, because it can simply not compute if it goes above 255. And the same method we do for the low colors, for the low values of the pixels. This was the high values of the pixels, the light ones. This is the dark ones, and it's approximately the same, to be quite honest. As it has a 20 value gap between, for example, here it has a gap from 100 to 120. Then I make small changes. It is completely optional though, but I only found it to be more smooth if you do that. Which takes the little darker light colors and the little brighter dark colors, and only add 10 to them. So we have 4 small gaps of 10 in the value. There is no pixel that has that value. And we do the same for the green channel and the blue channel as well, and set the output to be equal to red, green, and blue respectively. The next filter is a pretty easy filter. It's the log filter, log image filter. You only have to take the log of the values that each pixel have. Alright, and here is how it looks. It looks pretty dull. It's only black. Let's face it, it's only black. Pardon me for being a curious George, but I had to cheat a little. I had to multiply the log filter to see what actually happens if you have a higher value in the log. And here it looks like. Now it actually has some output that is not primarily black. It looks pretty rad. Alright, so let's get to how I did it. It was actually pretty simple. You take one for loop, like you did in the invert. You make a double inside the for loop, named pixels double or whatever you want to call it, and set it equal to the image. Then you set the output equal to the log of the pixel stubble that you just created. And if you want to cheat a little to see some actual image, then you can make this, multiply it with the adjustment or just a number. I made an adjustment right here, and it's called in here as well. And right here I make the adjustments to it. Alright, here we have the exponential function. Like the other one, it's pretty simple. It's pretty much the same approach. Here you only take the exponential function instead of the log, and you get this. I also had to be a little curious about this one. What happens if I divided it with something, and it suddenly becomes more rainbowy. Yay! Oh god damn it, I hate myself. Alright, let's have a look at it. The adjustments is a float. And here you see I have the double, like in the other one, which is equal to the image, and the output is equal to the exponential function of the pixel stubble divided with adjustment. And this one is completely optional. It's not part of the assignment. It's just because I was curious, George again. Here you manipulate the adjustment, and you manipulate it only with a 0.1, hence why it's a float. And yeah, that's pretty much it. This filter is the gamma correction, and here is what it does. You can change the values by the up and down key, like this, yes. And let's see some of the code for it. First of all, in the header file, we have a float called gamma, and we have unsigned char RGB. And in here, we set the gamma to be 1.0. This is the one we can change the value of right here, right down here. Yeah, it changes by 0.01, very low. And it can only go from 1 to 0.1. Yes. Right here we have two for loops, one for the y-axis, one for the x-axis, and we set the RGB to be equal to the red channel, green channel, and blue channel respectively. We set the output to be equal to the three different color channels in the power of gamma. Here we have a pretty easy to understand filter, image filter, the RGB to grayscale. As you can see, the image is in grayscale now. You have no colors, it's only black and white and gray tones, of course. So how did I do it? It is pretty simple. Note that the RGB scheme has got to be changed to luminance, as it is a black and white picture. Then you take two for loops, one for the y-axis, one for the x-axis, and then you set the output to be equal to all the different color channels, pixel blah blah blah, 0 at last, 1 at last, and 2 at last, red, green, and blue. You plus it with each other, and at last you divide it with 3, which is the number of the different channels. Then you have a gray tone scale. Now that we have the grayscale image from before, we can add some salt and pepper noise to it. Now what is salt and pepper noise? It is a large number of black and white pixels that has been added randomly to the stage, placed completely randomly, as you can see here. And for each frame, it places the white and black pixels a little differently, so it adds this noise. Alright, let's see how I do it. From before, we know that we have to make a grayscale image like this. That's exactly how I did it before. This is only an expansion of it. Now I make an integer called random num01. You can call it whatever you want. And this goes this creates a random function in modulus with 100, which gives a random number between 0 to 99. If the random number we just created is less than 5, then we run this function. That means it only do it approximately 5% of the time. Then we make a new random number called random num02, which is equal to a random function again in modulus with 2, which gives us between 0 and 1. That's pretty simple, but that's because I want both. That's for the black and white pixel. If the random number is equal to the new number, random number is equal to 0, then the output will be 0, which is a black pixel. And else if it's 1, then it's 255. That means 5% of the time it will generate a pixel that will either be black or white. Alright, here we have the grayscale to binary. What binary is it's only black and white, no gray tone scales at all. Alright, you can see it here. You can increase the threshold a little, or decrease it, I can't remember what's what. Like this. It's pretty rad. Alright, let's get to how I did it. First of all, you know the code right here for the grayscale image, and here I made an adjustment which can be replaced by a random number. Any number would do, between 0 and 255, of course. Then you say if the output is higher than the number that you put in here, then the output will be 255, or else it would be 0. The adjustment, I have just made an adjustment layer right here that I set to 100 at starters, and then I can change it right here where the adjustment is an integer right here. Now we have the alpha blend. What it is a fade between two pictures or videos, or a mixture of both. For instance, we have our video feed here, right here. It is completely transparent. As I will push the up button, it will become less transparent, and the other image that I have in store of me in a suit will become much more transparent. Like this. Yay, that's me in a suit. And I will go back. I really do have a bad sense of humor. Anyways, let's get to it. Let's see, we have this off image that we call image texture, and we have a new float called alpha. In here we set the alpha to be 0.0, and we load the image from a specific folder here. I have it right here. This is the folder where I keep all my files for this one. Inside the bin, inside the data, and there you have it. Alright, then we load it into the image texture. Alright, you can resize the image if you like, but I already have resized it before in Photoshop, so I don't have to. But I left it there just to let you see that it's possible. Alright, now we have the in total pixels like in the other ones, and a single for loop. We have gone through that a couple of times, so I'm not gonna do that again. Then we have the unsigned char pointer called video and image, which is similar to the former filters unsigned char pointer pixels. This fetches from the video feed, it fetches the pixels, and from the image it fetches also the pixels. The output is set to be equal to image times alpha plus video times 1 minus alpha. Now what this does, if alpha for instance is 0.7, Then we minus 1.7 with 0.7, and we have 0.7 right here. This gives 0.3, which makes it 1 in total. Alpha can only go from 0 to 1, and it's added to it, then it you get the image. Here we have the normalized RGB filter, which is pretty damn ugly in my opinion, but that's how it looks. The formula for the normalized RGB filter is the red channel over the red channel plus the green channel plus the blue channel multiplied with 255. Let's have a look at the code. Alright, here we have a double, which is part of a fraction, part of the fraction I just explained, and the unsigned char, normalized R, normalized G, normalized B, which is the normalized red channel, and so forth, and RGB right here. First we set the R and G and B to be the red channel, green channel, blue channel respectively, and then we create part of the fraction, which is R plus B plus G as normalized RGB. Then we calculate the normalized R, G and B by simply dividing it with this fraction, R over R plus B plus G, multiplied with 255, and here we take G instead of R and B instead of R. Then we simply just output the normalized color channels. Alright, the next channel is probably the most ridiculous and useless piece of filter I have ever come across in my opinion. It is the RGB to HSB filter, and what it does is it takes for each pixel the red channel and replaces it completely with the hue of that exact channel. Then it takes the green channel and replaces that with the saturation, and it takes the blue channel and replaces it with the brightness, which has absolutely, in my opinion, as far as I know, no relation to each other. So that's why the outcome is so weird. Look, it becomes more red. It makes no sense. Anyways, let's get to it. In here we have a double named U, saturation and brightness, and unsigned char named RGB. Alright, in here we set the RGB to be the red channel, green channel and blue channel respectively, and we set the big R to be the small R's, the small color channels. Yeah, you get the image, you get the picture. Then we have a formula which I will not get into right now for U, and we have a formula for saturation, and we have a formula for brightness, which we set to be equal to the red channel, green channel and blue channel right here. This is the Acos image filter. Alright, this looks kind of inverted, similar to the log and the exponential function image filter. We also only have to take the Acos of the different pixels there is in the image. But the outcome can be very different because you can't take the Acos of a really high number such as 255. You have to apply it to a smaller number. So we have to divide it with something, and when the Acos has been calculated, then you have to multiply it with the same number that you divided it with. So the different numbers that you can divide and multiply it with actually has a lot to say about the outcome of the image. I made it into an adjustment layer so that you can see the different outcomes that it can have. Alright, here we go. It actually looks kind of funky, this one, and then it kind of fades out on black here. Alright, let's get to how I did it. First of all, we have to deal with small numbers, so we have to make floats. Pixels 0, 1, pixel 0, 2, pixel 0, 3, and the last one, which will be the outcome, pixel Acos. Alright, so the first process is we take the pixels 0, 1 to be equal to the image itself. Then we take the pixel 0, 2 to be equal to the pixel 0, 1 divided with the adjustment that I've set to 100 in this case, and you can adjust it right here. And then you take the Acos of pixel 2 right here. Then you set the pixel Acos to be equal to pixels 0, 3 times adjustment. So you multiply and adjust. And right in between you take the Acos. Then you set the output to be pixels Acos, which is the final output. Alright, here we have the increase or decrease color depth. This is what happens. It looks sort of right. And if you type down, here we actually get some kind of a great contrast, like in a simple contrast. Yeah. You're gonna get the picture. Alright, let's get to it. Let's see the code. Alright. I've made an adjustment layer just like the rest, so I will not go through that. The RGB is set to the red channel, green channel, blue channel respectively, and then the new R, new G, new B will be calculated here. This is some formula I found for it. You take the B here, plus it with the adjustment divided with 2, and then you plus that with the B plus the adjustment divided with 2. You can actually just say this in the power of 2, but I can't remember why I didn't do that. But it might be something with the power of has to take in doubles. But yeah, then you put all this in modulus with the adjustment and minus it with 1 at last. And you do that for all the different color channels. Then this is again a precaution. We don't want the value to be less than 0, and we don't want it to be higher than 255. And then at last we set the output to be equal to the new red channel, green channel, and blue channel. Yeah, adjustment right here. We have set it to 8, and this to 4, so it can't be divided with 0. For the U, I used a built-in function to make it look like this. I only push the up and down button to change the U. Alright, so how did I do that? I have a U here that I call here as a float, and an off color image color. The U I set to minus 45 right here, and you can change it down here. Here I call the colors to the image color, the different color channels to be equal to the picture's actual respective color channels. And I set the U, this is a built-in function, and this is the one you can manipulate, and I will set that in relation to the built-in function. I will then call the output to be equal to the image colors, to the red, green, and blue channel respectively, like this. I use the same approach for the saturation change as for the U shift. I used a built-in function to create this as well. It looks pretty weird, but that's apparently how it looks. It goes from really intense colors to almost grayscale. It is a grayscale. It works exactly like the other one. We have it set to 135 this time because we want to start in the middle. But we set the saturation instead of the U, which is a built-in function, and we set it in the relation to the saturation, which is just a hue shifted name to saturation. It is exactly the same. So the next filter we are gonna make is the sepia. Alright, as you can see, yeah, I kind of hoped they were a little more yellowish, because that's how I imagined sepia. But this is a predefined formula for the sepia tone. Yeah, let's take a look at it. In the header file, we call the double sepia R, sepia G, and sepia B, and we have an unsigned char RGB. Alright, then we have two for loops for the y and x axis, and RGB is set to the respective color channels. Sepia R, sepia G, and sepia B is defined as this. These are some formulas that are found for the sepia tones. Yeah, this is some precautions to make sure that the values don't go below 0 or go above 255, any of them. Then we set the output to sepia R, sepia G, and sepia B to find the new values. This is the pastel colors filter. Let's see. Yep, it is pretty pastel. Unfortunately, every color in this image is pastel, so it seems a little dull, if you ask me. But yeah, it kind of gets the picture. As for the sepia, we also create some new integers, a new red channel, a new green channel, a new blue channel that we are gonna output. We set the old red, green, and blue channel to be equal to the red, green, and blue channel, respectively. And the calculation for the pastel color channels is the red channel divided with 2 plus 127. Unfortunately, we cannot make an unsigned char into this calculation, so we had to make a temporary red, green, and blue channel for each of the channels. This is just a precaution. It says that if the color is higher than 255, then it should be 255, and if it is below 0, it should be 0. And here we print out the pastel colors, both for the red, green, and blue channel. And now for the pink color detection, the last point processing filter. It takes all what I have defined as pink in the script and print it out as white, whereas everything else is printed out as black. As you can see, my lips is probably a little pink, which is why it's printed out as white. I have a t-shirt right here, 2 seconds, that is pink, or partially. Alright. It says love in Danish if you wonder. Useless information, but hey. What I think is really rad is it prints out the letters really clearly. And that's why I really like this filter. Alright, let's see how it works. Alright, in here we have the integer pink and we have the unsigned char RGB as usual. The integer pink is the pink color that is that we define. Alright. RGB is again equal to the respective color channel, and we define here what pink is if R is higher than the red color channel is higher than the green color channel plus 90, and the red color channel is higher than the blue color channel minus 20. It should print out 255 or white, and if not, it should print out 0 or black. And then it goes through this, stating that the output should print out pink. Here is the mean filter. As you can see, it is a little blurred. it is a 3x3 kernel. You can especially see it is a little blurred if you look at my hair right here. Yeah. And here is how we do it. In the header file, we have a kernel, which is an array, a 3x3 array. And right here we have an equal sized array named mean, which contains all the values that we are going to apply to the image filter. All the values are 1 divided by 9 because there is 9 different numbers. The middle value is the value in focus, and the point of neighborhood operation is that you have a pixel in focus in the middle, and then you are gonna apply a specific filter in relation to the value of the neighbor pixels and the pixel pixel in focus have. Alright. So now we know the values in the array of the mean. Now we're gonna apply it to the kernel. We do that by doing a simple double for loop, and we have a ky kx, which is basically the same system as the yx for loop that we have done before. It counts from 0 to 2, 0, 1, 2, which is 3 values, exactly like the one here. You have 3 times 3, and we do it 2 times, so we get 9 in total. We apply this. What this does is that it takes those values into the kernel right here, so we can use the kernel later. Alright, here we have 3 for loops, one for the y-axis, one for the x-axis, and one for the color channels. When this runs, it brings out a black background, a black color, to be quite honest, on the output, and then it runs the kernel right after it, which counts from -1 to 1 because it wants to have the 0 in the center, which is the pixel that is in focus. It is exactly the same size as the one up here. This only counts from -1 to 1 instead of 0 to 2. And then we're gonna apply it to the output that is defined up here. This formula, which is the formula that is gonna add the kernel, gonna add the blur effect to the image. This is another kind of mean filter. It is a 7x7 disk instead of a 3x3 box. As you can see, it is a lot more blurred as the other one. I don't even have to go near it to actually make you see it. And it lags a little because it has a lot more information to process. Let's see how I do it. Instead of a 3x3 array right here, I have a 7x7 array. And likewise with this one, it is an equal size with the header files array, and it has 49 informations right here. The purpose of a disk is it only takes the center values from the pixel in focus. These values out here, the zeros out in the sides, they are not even, they have no influence on the pixel in focus. So it kind of like makes a disk right here. It has 25 values right here, which is why we divide it with 25. And up here I have made another one, which is a little more aggressive, which is divided with 37 because there is 37 values. I have not shown that because it takes a lot more time to process. Let's see, instead of 2 we have 6 here because we count to 7, and from 0 to 6 there is 7 numbers. And right here, let's see, we plus it with 3 instead of 1 because we have a little larger disk, and that is the middle value. This is a Gaussian blur filter with a 7x7 kernel, which is why it also takes a lot to process right now. It's why it's a little slow. You can see how it blurs, and let's see how I do it. Alright, first of all, it is exactly the same right here, and the only thing that has actually changed is the values within the array. Instead of having only one, we have different numbers assigned to it, which kind of like from the middle, from the center kernel, from the center pixel, it has some kind of a gradient around it. It goes from a high number to a low number, and to an even lower number if you go up to here. Yeah. So it kind of has a gradient blur around it, and there is 140 values inside this. So we divide it with 140. It is exactly the same as the other one, right here, right down here. But yeah, it's only this that has changed. This is a Gaussian edge filter. It has a 7x7 disk, which is why it is a little slow. It is very interesting, I think. Let's see how I do that one. Exactly like the other ones, we have a 7x7 array. This code is exactly the same. The only thing that has changed is this one again. You can see at the left side we have all minuses. It is if you take in comparison to the other Gaussian blur filter, we have the exact same numbers beside the middle row, because we want to find the edge. Then we have all positive numbers over here and all negative numbers over here, and that is why we can find it. Here we have the different Sobel filters. The middle one is the horizontal Sobel filter, and the right one is the vertical Sobel filter. I actually think it's quite interesting. It gives it a little 3D effect, I think. Let's see how it's done. First, the test app. It's actually this exact same approach as the mean filter. The mean filter with a 3x3 box. We only do it 2 times this time because we have 2 images. We see that we have the kernel array with a 3x3 size, and the only thing that actually has changed here is not the code here. That's exactly the same, just done 2 times. It's only the values inside the array here. We have -1, -2, -1 on the top of the horizontal, and 1, 2, 1 on the bottom of the horizontal. And likewise with the vertical, just vertically instead of horizontal. Between the Sobel and the Prewitt, there is not much difference. Personally, I think there is none. I really can't see the difference, but there is a few modification in the kernel, which is actually the only difference. The header file is exactly the same, and the below code right here is exactly the same. Here we only change the number 2 with 1, and then we have the Prewitt. Alright, here we have the median filter. It's an interesting way of blurring an image. It is a bit different than the mean filter in the way it approaches the blurring. Whereas the mean filter finds the average of the pixel in focus and the neighbor pixels. This kind of sorts the different values. It has 9 pixels, depending on how big you make it. But if it has 9 pixels, for instance, it sorts them after from which one is smallest and which one is largest, and then it finds the middle of those and takes that and brings that out. That's how it works. I'm actually quite surprised it didn't lag as much as I think, because it runs through a lot of data. Yeah, let's have a look at it. First of all, we have to make a new function, which is called selection sort in my case, and then it pretty much look the same. Here we make 3 jars, one for the red, green and blue color channel, which is a 2-dimensional array, 3 times 3, which is 9. Then we make a 3-dimensional for loop and set output to be equal to the image, the pixels we get from here. Then we make a 4th-dimensional for loop. The first 2 is the y and x axis, and the second 2 is actually to create some kind of a kernel to make the neighbor operation. It's an easier way to make it, besides making a kernel. It goes from -1 to 1, from -1 to 1, which means it is a 3 times 3 kernel. Then we set the median array from each different color channels to be equal to the output with these calculations in them. Yes, and then we make a selection sort, which will sort them, and we say there is 9 different values that we have to sort between, and then we sort them each individually right here. This is our selection sort function, where they this is a simple swap function. It just have 3 different things it needs to swap, because it has 3 colors, RGB. And then it prints out the output to be the median array for each color channel to be 4, because we have 9 different values and we start from 0 and go to 8. So 4 will automatically, as you can see here, be the middle value. In the median, you have to take the color in the middle of the row of the selected 9 colors. In this one, you actually only have to take the max value. That means the brightest color, which is why this is so much brighter than the last one. So let's have a look at it. It's exactly the same code. This time we only take and write 8 instead of, because it goes from 0 to 8. Alright. Now that we have the median and the maximum value, this one is also fairly easy, because this time you're gonna take the minimum value, which is the blackest value there is. As you can see here, the blurring is getting a little darker, and that's because of that. This is the minimum value. The only thing you have to change is to make these 3 numbers into zeros. Yeah, this is the Emboss filter. It's also kind of interesting. That one actually looks a little like the Sobel and Prewitt, but there's a slight difference, I think. The purpose for these filters is that it gives it a little 3D effect. Also in this one, this is actually really great for Grayscale. I saw it on a Grayscale, this one. It was really good. Let's have a look at how I made them. The first one, the one in the middle, is this kernel, has these values, and the last one has these values. Then I simply just use the same approach as for the mean filter, 3 times 3, and the Prewitt and Sobel. Alright, here we have an interesting noise filter built on neighborhood operations. This is the Gaussian noise. It is primarily built with a Gaussian blur and a salt and pepper approach to it. It is pretty interesting, I think. It's pretty interesting. You can still see me pretty clearly, I think. behind all those colors. Anyways, it's a little slow because it has a lot of information to process. Formerly I made it with a 7x7 kernel. This time I only made it with the 5x5 because I needed it to run a little faster than the previous ones. This is the new kernel I have made, and we also had to change the values from here and here to 4 instead of 2 and was 6? Yeah, it was 6. So it runs, it counts to 5. It counts to 4 from 0. That means 5 times, which matches the size of the array. All right. Down here, when it has when it has run through the 5 for loops here, these 2 for the kernel, it will make a new integer called random number, which will generate a number between 0 to 99, kind of like, or exactly like the salt and pepper noise. If the random number is lower than or equal to 3, which is really low, then you run this if statement. If the random number in modulus with 2 is equal to 0, meaning half of them, there is only 0, 1, 2, 3, and half of them, that means there is a 2% chance of that happening. The output will be the image times the kernel, and else the output will just be the image. This is the diffuse filter. I'm not actually sure exactly what happens here, but that's the right kernel. As far as I can detect, there is a blur. There is definitely a blur, but I think I also can detect the stronger right color. I'm not quite certain though. Let's have a look. Maybe there is. I can't quite tell. But this is the diffuse filter. Let's have a look at how it's made. There's not much difference from that and the mean filter and the Sobel and Prewitt and yeah, all those filters with the 3x3. It's exactly the same code right here, and it's only this one that has changed. It is a what's it called? A line through from the top left corner to the bottom right corner with 1 divided with 3 because there is 3 values, I will assume. But it's precisely like the other ones. You just have to put some other values inside the kernel, and it will make the effect. Here we have the edge detection for the vertical edges only. It's actually pretty cool. You can see that it's only the vertical lines that has been drawn, especially by my eyes, because they are mostly horizontal lines. I can also hold my hand like this, and you can see there is no edges on the top of it because it's horizontal. If I do it like this, you can see the edges again. Alright, so let's see how it works. It's pretty much like any other of the kernels I have explained earlier. This time I use a Sobel vertical kernel, and I pretty much, instead of just printing the output right here, I make a float called value, which is set to 0.0, and I set this value to be this formula as I used in the previous ones. However, the difference between this and the other ones is these 2 lines. It says if the value is higher than 100, the output will therefore be 255, or else it will be 0. Alright, what we have here is 2 altered images. The first one, which is the middle one, we already have clarified, and yeah, that is the grayscale to binary image. The reason I have the grayscale to binary image is because the dilation is supposed to be a filter to that one, and I want to show you how it affects the binary image. As you can see, the whites expand into the blacks of the image, which it is supposed to do, because if you have, it's kind of like a neighbor operation. If you have a black pixel, then you search around the black pixel for any white pixel. If there is one white pixel, it will write the black pixel as white. Alright, so now we know why the whites expand into the black picture, but how do we do it? Let's take a look at it. First of all, we have the grayscale, the RGB to grayscale. Then we have the grayscale to binary image, and here we have the dilation. Let's see. It runs through the y and x axis in a double for loop. It creates a float for each time it hits a pixel, then, and sets the value to 0. Then it creates a neighbor operation right here. Ky, kx. It runs from it has a 9. It goes through 9 pixels in total. And for each time it does that, it sets the value that we have created right here to be equal to the output divided with the 255. And here it says if the value is higher than or equal to 1, the output should therefore be 255, or else it should be 0. Alright, so why does it dilate right here? Because if you have, for instance, 255 in one of the pixels, then divided by 255, it automatically gives higher than or equal to 1. If you don't have, then you have nothing. Then you don't have higher than or equal to 1. So if there is at least one pixel in the neighbor pixels, one pixel that is white, then it will be white. Whereas the dilation expanded the white fields of the image, erosion does the exact opposite. It shrinks it in instead of expanding it, as you can clearly see here from the bitmap to the erosion. Now, how does it do that? Whereas the dilation only had to have one pixel, the erosion have to have 9 pixels that are white before it can print out white. Let's see how I do that. The only thing I actually had to change here was this. The value had to be equal to 9 before I could write 255. Yeah. The right top image is the binary image, and the left bottom image is the erosion, and the right bottom image is the opening. The opening is basically a binary image that has been through first an erosion and then a dilation. As you can see here, I wanted to show how it affected the opening, the erosion, to also make it send it through a dilation. So how do we do it? That is pretty simple actually. First we go through an erosion right here, and then we take the results from that and send it through a dilation right here. So on the right top right, we have the binary image again. On the left bottom we have the dilation, and on the right bottom we have the closing, which is the one we are focusing on right now. Here you can see the effect it has. These images is almost the same. This is just much more unsharp than that one. Yeah. So how do we do it? It's exactly the same. This is the exact opposite of opening. We simply just run through a dilation, and we run through right after that an erosion. So now for the boundary detection. On the top right we have the binary image. On the bottom left we have the erosion of the binary image. If you take the erosion and subtract the binary image from that, you get the boundary detection, which is on the bottom right. Let me show you how you do it. Simply you make the erosion first, and then you take the erosion and the binary image, and this is the binary image, and subtract the erosion from it. And now for the Grassfire filter. First of all, I have made the image into a binary image, and then I have found the different blobs there was in the picture and assigned them a different color, a randomized color, so it blinks all the time. It is pretty rare, I think, but there may be a problem in the code. I don't know if it's Microsoft Visual Studio that just thinks it is an infinite loop, or it actually is an infinite loop. You be the judge of that. But if there is too much white in the picture, let me just show you, then it crashes down. Alright. Let me try to explain the code. First of all, we had to make the image into a binary image, which we do here. We have set the threshold up a little to make it not crash all the time. And then we call for the Grassfire function right here. What we do here is we scan through the image pixel for pixel, and then if we find a white pixel, this if statement, if you find a white pixel, it will run these two. The color is set to be equal to a randomized color between 30 and 249, which this makes. And then it calls for the Grassfire function, which have the output, x, y, and color inside it. And the Grassfire function is also here. And right here we have the Grassfire function. Then it said if the pixel is white, we just found the white pixel up here, then it will assign the white pixel the color, which is this one, which is a random color between the thing I just said. Then it runs the 4 different if statements, and what these if statement does, I can try to explain the first one, and then you kind of get the point for the next ones, I think. It says if the pixel right next to the white pixel, the pixels that we have in focus, is lower than the width, and the output for that pixel, for the right pixel right next to it, is equal to 255, meaning a white pixel, it should run the Grassfire function. The Grassfire function will be applied to the pixel right next to the white pixel that we had in focus, and it will assign that pixel a color too, and therefore also run the 4 different if statements again and again and again and again. So in short, what it does is, and the 3 other if statements is for the other directions. So in short, what it does is it kinda, if you have a white pixel, it will search for if there is a white pixel above or below or right next to it or at both sides. So, and then it will run the Grassfire function at them as well. So it will kinda expand until it reaches the black border of the white blob. Regarding the resize filter, I have made it so it both can be scaled and stretched, like this one. It is, As I recall, it is 65% in the width and 75% in the height. Let me see how. In the header file we have made two floats, a scale value for the y and x axis. And then we have assigned those two a different value. You can see them as a percentage right here. You cannot make higher percentages than 1 because it will have influence on these ones as well. And these cannot be decimals. And they will be if they are higher than 1. I have not figured out a way to do that now. But right here, yeah. And then we assign those values to the new height, which is equal to height times that value, and new width, which is equal to width times the other value, scale x, scale y. Yeah, you kind of get the point. Then we have then we only run the two for loops that will bring out the output to run to the new height and new width. Inside these three for loops, we have made two integers, a new y and new x, which we take the y value and divide it with the scale value, the y and x value, and divide it with the scale value. And then we just put in the different new numbers right here, and we have the resize function. This is the rotation filter, and you can change it by pushing to the right and putting to the to the left. Alright, here we have it. Hey, we rotate it. Anyways, alright. First thing first, we have made a float that is called decrease that we set to 0 right here. That is why we start from the beginning. That one you can call, change in the key press switch case right here, and it will have influence in the equations right here. I will get back to that. First of all, we make two new integers that is equal to the center of the image, and then we make then we call the classical double loops and make two floats that each is the definition of the rotation. These are the basic equations for the rotation. Then we make two new integers called the rotated canvas for both y and x, that we set to the rotation plus the center. And then we this if statement makes sure that the image doesn't go beyond the border. That means beyond the width and height and 0, and yeah, you get the point. And then if it is true, if it is within the border, then it will make the output equal to the pixels, and we have to replace the y with the rotated canvas y and the rotated canvas x that is defined right here with the rotation right here. Yes, you get the point. That is how I made the rotation filter. As for the crop, it is a really basic filter. Right here I have made it a little more complicated than it actually is. I've made it so that you can actually crop it yourself by using the arrow keys. Yay, let's make a cowboy scene. Yeah, alright. The only thing you have to do is actually just type a different number in here than 0 and a different number in here than 0 to scale it from the top and the left, and you have to minus it the width with a random number, whatever you prefer, just as it is higher than the width, and likewise with the down here. I have made it so that you can change it yourself though, but that's all the numbers that you have to change in the crop. I will not go into how I did that. I will only show you the code. It is pretty basic mathematics. So now for the pixelate filter. What it does is it takes the neighbor pixel and replaces it with the pixel in focus color. So it looks like this. I now enter the world of Minecraft. Yes, it looks beautiful. I've done it so you can adjust it yourself. Just by making an adjustment, and right here adjustment, and key, and a switch case for it. What you do is you make two new integers, one for the y and one for the x-axis. Then you set it equal to the y or x minus the y or x in modulus with the adjustment. And the adjustment can be anything from 1 to, I don't know, a lot. Just do something. Just write a number or any number. Then after that, you take the new y pixel and x pixel and you insert it in here, inside the image that the output is gonna be equal to. The pointernized filter is sort of like an expansion to the pixelate filter. You still make it pixelated, but this time you make a jitter. Sort of like you only write every second pixelation. Yeah, I will show you how you do it. First, I've also made an adjustment to this so you can see how it looks when it's scaled. Alright, as for the pixelate filter, we do the same here. But this time in the pointernize, we make two new integers, which is num01, num02, that we set equal to the y in modulus with the adjustment times 2. And here we say that if the num01 is lower than the adjustment and num02 is lower than the adjustment, the output will be the pixelations. Otherwise it will be 0, which is black, which makes the jitter. You can sort of like see it if you, for instance, if you have adjustment equal to 4, then you will have 8, y in modulus with 8 right here, and x in modulus with 8 right here. And the adjustment will be 4 here. It sort of like counts from 0 to 7, and the 4 is in the middle. 4 is in the middle. So you print this out at the first 4 pixels, and for the next 4 pixels you print this out. This is the ripple effect, and here's how it looks. Beautiful. You can adjust it just like the other two I just showed. I will not show you that again. How I did that was there is a calculation for the ripple effect, which is this one, but I had to make it into a double because an int can't calculate this one, and a double can't be in this one. So I set the new x to be equal to the x double that I just calculated, and I set the new x inside this one. Alright, this is the twirl effect. It is so fucking ugly. Oh god. Yeah. It is actually pretty difficult to explain because it's just two big calculations. One for the y and one for the x rotation. Here's the calculation, and it consists of parts of the above doubles and integers. As you can see, the radian is right here, the cal fits right here, the rotation is right here, the x diff there, the y diff right there, the radian also right there. It is one big calculation. This is precautions that we should not have the twirl effect to go outside the borders to yeah. So we just do that. and then we put the rotation Y and rotation X in inside this one to make it work. This is the accumulate image filter, which I actually would rather call the directional blur. As you can see, probably mostly on my speaker here, there is a directional blur on the x-axis, horizontally aligned. Yeah. Moving on, how did I do it? Simply enough, instead of using a kernel to calculate the average of the neighbor pixels, I did a long calculation right here, where I took 9 different values. 9 on the here, for instance, I have pixels, and here it takes x and minus it with 4, which means it goes 4 back on the x-axis, and at the last one it goes 4 further down the x-axis. Yeah, you get my point. And there is 9 values in total here, so I take the average of that. I take the mean value of that, and that's why I have a horizontal directional blur. I divided all of 9. Yeah. I do it for both the red, green, and blue color channel, and then I print it out like this. The arithmetic constant add subtract is actually pretty rad, I think. In contrast to the alpha blend, you have a picture though. You have a picture in here and a webcam feed, but instead of fading it into each other, you add and subtract it in relation to each other. In the first image here, we actually add the texture that I have. You can see it right here. 2 seconds. It's right here. Inside the bin, data, and texture. It's this one. It's a pretty black actually, but also it has some white texture in it, and that's the white text that you can see because the black is just close to 0. Yeah, but you add the webcam feed and the texture to each other, and here you subtract the texture from the webcam feed, and here you subtract the webcam feed from the texture, which makes it kind of inverted. Yeah, I actually really like this one. Yeah, how do I do that? Like the alpha blend, I load the texture from the folder that I just showed you. It's called texture.jpg, and I have the image texture right here. Yeah. Then I simply just make some outputs that is equal to the video plus the image, or the video minus the image, or the image minus the video. Video plus the image or image plus the video is actually pretty much the same, you can imagine. Then I make some precautions that the value of each pixel cannot go above 255 or below 0, to make sure that it's not given any weird colors, or yeah, you get the point. And then I simply just set the output to be equal to these outputs that I made here. And here is another filter, the Neo-noir. It's kind of like a binary picture, but this time it brings out the red channel as well. And if you look closely, it also has some gray shades to make it a smooth transition between the black and white. Yes, so how did I make this? Alright, let's take a look at this one. That's interesting. We make a float that is named the sum, and it should be equal to all the different color channels combined plus 0.0001, which why I add this to the equation is because I have to divide it with something afterwards. Alright, then we make 3 integers RG and B, which is equal to the respective color channel. And then we have a lot of then we have an if statement that states I will not go in depth with that. In fact, what it does is it finds the red channel and prints it out. It defines what the red is, and then it prints out the red and make the green and blue channel 0, which is black. And if not any of these are true, then it should check if the sum is higher than 400 and the sum is equal to all the different color channels combined, which is 200. If all the pixels if it is a white pixel, for instance, in all white, then we have 255, 255, and 255. That is a lot above 400. It's approximately in the middle of the 3 different color channels combined, 400. So if it is a light color, then we should print out 255 for each color channel there is. And if not, we should print black. Alright, now for the little blurry effect with the gray transition, we have we make a float right here. I will not go into we make a float and set it equal to 0. And here we make some kind of a kernel without making a kernel. We implicate a kernel by making the double for loop ky kx and set it to from -1 to 1, from -1 to 1. That makes a 3x3 kernel. For each pixel there is in this kernel in the neighborhood pixels, we should add the output from that pixel to the equation for each color channel there is. If the output is higher than, if the red channel is higher than the green and blue channel combined, it should just say the sum is 0. Why we do this is because we don't want the gray to actually infiltrate, to make a smooth transition between the red and the white or black. We simply want the red to just be there without any gray infiltrating it. Else if the sum is higher than 3 times 3 times 255, which is and the sum is lower than 6 times 3 times 255, it should print out gray. Now what it does here is it says that in between, if there is in between 4 colors, 3 colors or 6 colors in the area of the neighborhood that is that is white, then we should print out gray.